Okay, so today's topic will be about the registers. We are still in chapter 4. So what are the registers, why we need to use them, and what's the point of using it? In previous classes, we discussed about the flip-flops, or we discussed about the sequential circuits. These sequential circuits, there must be a storage element. That storage element is called flip-flop or latch. Latch, SR latch, D latch, or SR flip-flop, D flip-flop, T flip-flop, JK flip-flop, and we are all aware how these elements are working. The flip-flops are working only for 1 bit. That's what we used to do. And we know the construction, how the flip-flop looks like inside, we know how to do it. So now we know first how to do the basic logic diagram based on the transistors, based on PMOS or NMOS or CMOS transistors. So we know how to do the basic logic using NAND, NOR, and NOT gates, right? Then after that, we know how to implement from NAND and NOR, how to implement AND and OR. This is in hardware, right? Then we can create our chips. This is the chip AND, this is the chip OR. Then after that, we make some developments like we can create SR latch, which is a combination of NANDs or a combination of NORs. Then we create a chip, it's called latch, which is SR latch. Or we can create a chip D flip-flop or T flip-flop, JK flip-flop. So we can create all of the devices. Now we are trying to go from simple to be more complicated. So we create a block, then another block, and another block. So the flip-flops, again, for 1 bit. However, how about if we have a group of bits, which is called registers? So there are registers, for example, depending on, we call it N bits register, depending on N number of flip-flops. That register, for example, if you need to include 1 byte, we know the 1 byte, which means 8 bits. And that 8 bits means there is, in this 8 bits register, there is an 8 flip-flops. So that's the point. Then in the registers, it's actually been used a lot in the assembly language. As you will go later in another course, it's called microprocessors. And that in microprocessors, you will use assembly language a lot in programming. So that's microprocessors. You will see you need to use registers, move registers, write on the registers. Then what's this register, which is what we will discuss here in this class. Then later you will learn how to program using that one. So registers is basically an element, or like we can say kind of memory. How we can create this, which is basically by doing grouping a group of flip-flops, like for example 8-bit register, 8 flip-flops, group them together, put them inside a block, and that block will be called a register. Then that register you can do our programming that we will see later in different courses. So if this one is connected to a clock cycle, a real clock cycle, like as we used to say the clock in the past lectures, like this clock cycles, this will call a register. Why? Because this clock cycle, like tick-tock, it will store the data. That's what it is. However, there is another type or some type of the registers is called counter. This is a still register. This is a special case of the registers. But this counter, the clock is not like tick-tock. The clock, you have the control to do the clock. It's like counting. So you will count how many people are entering the room. So you'll see 1, 2, then maybe you wait 10 seconds, 3, wait 1 minute, 4. So something like that. So it's not necessarily to that clock will be, or to the gates, or no longer will be called clocked. So you will control them, or you have access to them based on an input, an external input. It's not based on a clock cycle as we see previously in the registers. In the registers or in the past, these clocks most likely comes, it's like as a watch. It comes from what's called an oscillator. That oscillator will produce a clocking cycle with a certain frequency. It can be 10 kilohertz, sometimes 10 megahertz, etc. That clock cycle, it's based on that device. That device will produce a periodic signal such that 10,000 times per second or 10 million times per second for 10 megahertz. So we will see 10 million times of this uniform per second. This is the regular clock cycle that's been used, can be used in flip-flops or even in the registers. However, for the counter, you have the control. You have a push button, for example, so you'll press 1, make update, press 2, make updates. Again, it looks like you have a counter, the regular counter that you have, press 1, 2. So you have the choice to determine when the next update will happen based on your action, which is the push button. That's the difference between the counters and the other registers. The counters, you have the choice to press. The registers, you don't have. It's already been connected to an oscillator or to connect it to a device that produces a time. And again, that device or that signal, we call it clock. When there is a clock, we call it synchronous. And this is the same way that we know in the past. However, if it is asynchronous, which is not connected to the clock, then you need to, which means you will press this. Or there is an external counter, like for example, a sensor. A data comes from sensor. That sensor can detect if there is an event happen. Then that sensor will give you a signal. Can be as a gates, connected to the gates. It will not be called a clock. This is asynchronous. Remember when I discussed earlier of this course about the sequential circuits, I said there's synchronous, there is asynchronous, or non-synchronous, not synchronous signals. Okay? So whenever you read or you hear about 8-bit register, there's 8 flip-flop inside it. 6 bits, 6 flip-flops, 4 bits, etc. That's it. It's just like a tool, or inside it's a block or a chip, integrated circuit IC. You will see a combinations of flip-flops inside it. Then later, we created registers and we modify on them to make a combination of registers to create a memory. Then we can expand it to make our different several designs. Let's discuss some small demonstration example, like 4-bit registers. 4-bit registers actually is so simple. What we have real life, maybe 16 bits, 8 bits, 32 bits, 64 bits, like the operating systems that we have, like 64 bits, 32 bits. But for demonstration purposes, we will discuss a small, and if you understand the small, then the address will just be an extension. So if you understand the 4 bits, you know the 8 bits will be just super easy to understand. So we have one type for 4 bits register, which is using, this will be called parallel. You will see, here is the inputs, D0, D1, D2, D3. This example is using D flip-flop. Sometimes it can be using JK flip-flop, sometimes using other different type of flip-flops. So basically, we will assume we have a 4 bits register, 1, 2, 3, 4. And there's 4 outputs for storing this signal. Here we have for read, here for writes, here for read. Then here we have 1 bits for clock cycle to tell you when the update will happen. Then the other clock, which is for clear, to make it zeros, everything 0. So by making observation, this is how the chip looked like outside, how it looked like inside. That's what we have here. So we have D0, D1, D2, D3. It will be updated based on the clock. And we know how to do the timing diagram for each one alone. Now we are doing it with each one. We are doing with each one as standalone. This is the first point. The other point, when you let's recall the second exam question. There was flip-flops and there is output Y for each one alone, like Y2, Y1, Y0, right? Or Y2, Y1, Y3. That one, if you want to group it, you can say that one is 3-bit register, because each one has different distinguished outputs. But even though it was 3-bit register, but it was connected to the same output, to the same input X. So here, we know how to deal with flip-flop, but there is something new that maybe we are not used to it, which is the clear. Here are the clear section. So let's look here first here. D flip-flop, we know how to deal with D flip-flop. Clock cycle, we know how to deal with the clock cycle. We know it's flip-flop because it's triangle, and there is no bubble here, so it's it's rising edge, which is rising edge or positive edge flip-flop. Then the clear here, you will see a bubble. So clear makes everything zeros. When we press the clear button, we will make everything zeros. So, but there is a bubble here. And that bubble means it's active low clear. What does this mean? If clear is 0, this means it will work. It will make everything 0. If clear is 1, it will not work. It's active low. So the bubble means active low. Active low. Oh, sorry. Active low. So when clear is 1, nothing happened. When the clear is 0, event occurred. What's the event? Make everything 0. So how we can realize this? Where there is bubble, and when you look here, there is bar above this symbol. So the bubble and the bar, this means it's active low. Okay? And this happens because many times in real life hardware practical applications, the clear will be active low. This happens in many times, many applications. This is the common, most likely common. Active low clear. So let's assume this scenario. Let's assume the inputs D0, D1, and D0, D1, D2, D3, all of them like this, 0, 1, 1, 0. And let's assume these inputs are not changing at all. They are constant inputs. So we have this signal. We have the clear signal. We have clock signal that will make updates. And we have Q1, Q2, up Q0, up to Q3. So the first point, the clear is 0. When the clear is 0, this yields to make it clear the signal, which is active. Clear is active. Since it is 0 and it's active low, this will make a clear all Qs. What does this mean, clear all Qs? All Qs will be 0. All Qs will be 0. Therefore, we start from 0, 0, 0, 0. Why? Because there's a clear button has been pressed. Sometimes starting from now, you will not see in the question assume 0 initial condition. You will not read this. What you will see something like that in the clear, then you will understand no matter what's the initial condition, when the clear is 0, it will make it everything 0. Yes?
I think for one of the homeworks, what does preset mean? Does that just make it a 1?
Presets? Yeah, make it 1. Preset. Then, the clear has been cleared, so now it's 1. When it is 1, this means it's no longer active, the clear. Then, now disable it. Just cover this. Disable it. Like it's not exist. So don't look at it now. Because starting from this point, it will be 1. Then that's it. So this problem has been eliminated. Then the idea of using this clear, sometimes why we have this, because sometimes we didn't know the initial conditions, so I'm pressing clear to make sure everything is 0, then I'm ready for programming. That's the point of using it clear. That's one point. Other point, sometimes overflow can happen, something wrong happening with the memory, then clear it. This is the same way that when your computer is not working or your cell phone is not working, you restart this, right? This is the same way. You just restart. Restart to clear everything. So after this point, then we will worry about what's happening later. What's happening later, as we know, they are flip-flops, and that update will happen only at positive edge or at the rising edge. Where's the positive edge? Happening here. Here is positive edge, so the updates will happen here. So they will remain zeros hold until the updates occurred. That updates occurred, which is D0, Q0 will equal to D0. D0 is 0, D1 is 1, D2 is 1, D3 is 0. Then, I already updated the values. After that, is there any other updates? Clock? No. Let's assume that the clock has been stopped for some reason, or then it will hold. They will hold. So any updates, if there is any clock cycle, another clock cycle, you need to make sure if there is any update happening here. Which is the same as we know in D flip-flop. We know how to deal with this. We know how to deal with updates. We're already done with this in the exam and in the quizzes. So I think it should be all right, right? So just the demonstration here to let you know that the clear can be used to make the initial condition, for example. So we don't need to mention the initial condition. And the clock as the positive edge or negative edge, whatever, it will update correspondingly. So we already know all of this, but here we are grouping the flip-flops, more than one. Any question about 4-bit register? Then the same can be applied for 8 bits, 16 bits, etc. And the same way if the input is changing like this or whatever. Now we have some modifications or some other special cases of the registers, like we call it parallel load registers. Parallel load registers, sometimes here we have clock, clear, write, and read. But how about if I need this signal to be stored no matter what's the inputs? If I need, for example, to store the data in a flash drive and I need to lock this data. I don't want this data to be erased. How can I lock this data? We did a modification like this, parallel load. So we add something called load. So when load equals 0, retain the data, which means we can store the data, don't modify on anything. When load equal 1, register the data or start writing. So we can say when it is 0, don't write. When it is 1, write. So writing mode or reading mode. Something like that. So we add this special feature. It's the same as the 4-bits register, but we add this to make sure if we store the data, we don't want this data to get lost. Let's this be stored in read-only mode. Don't modify on it. So we can store this data without being affected. Okay? This is the modification that happens, so I'm not going to explain it a lot because it will take a lot of time, a lot of effort, but you can explore this, that when load equals 0, this is 0, this will make it 1, this will make it 0, then here this is 1, this is 0, so here is A0, and here is I0. So when there is 1, this will make A0 here, this will make it 0, then this will make it A0. Therefore, A0 will equal to A0. This means retain. Okay? Does this make sense? Right? Then the same happened for A1, A2, A3. Here I showed you a demonstration for first one, when load is 0. How about when load is 1? When load is 1, this will make it 0, this will make it 1. So I'm going to apply it here. This is still 0, here is 0. How about 1? This is 1. Here is I1. Here is A1. So since there is AND with 0, this will make it 0. This will make it I1. This will make it I1. Therefore, A1 will equal to I1, which means accept new data. So you need to figure out how to make the analysis, something like that. Okay? So if you see any kind of these questions, for example, in the final exam, and you see, for example, load, there's a timing diagram here, there's a timing diagram for others, like this, and you need to be aware how to do all of these techniques. Just understand it like load, what will happen. You don't need to memorize it. Sometimes just follow with this will make it easy to understand. Okay, any question? So this kind of registers, there's a clock cycle. Sometimes you can add clear as well here. You can connect them to clear, active low. So you can say there is a chip here, or IC, integrated circuits. Here we have D3, D2, D1, D0. Then here is the clock. Here is clear and active low. Then here is load. While the outputs Q0, Q1, Q2, Q3. So we can create this kind of register, 4-bit register. This 4-bit register can be done. Oh, load here. You can create it and go to the lab and do what you really want. Okay? There is some type of registers called accumulator. And that accumulator can be used to sometimes add some data or to store some data or count something and still keep adding some numbers. So that accumulator, since there is addition, we have adders. And this is the 4-bit register as I showed you here, which is the same as this one, as I draw it here. So if we draw the register like this, 4-bit register, that's connected to the adder 4 bits. So each output has 4 bits. There is inputs, there is a clock, there is a clear, and there is outputs. So our target is to make sure that we need, or with this accumulator, we have an inputs, so we need to count them. So we can use this, for example, in the bank. In the bank, you need to, for example, withdraw or get cash, maybe 1,000, something like that. So the banker will put them into a device that will count them. So if I have this amount of money, then I press the button, it will start counting. So this one example of the accumulator, how to count the money that you already inserted there. So this device, this is how it looks like inside, and actually it will be like as integrated chip. Here is the inputs with 4 bits. Here is the clear. The clock cycle sometimes can be internally or sometimes depending on several factors. Then here is the output will go to, for example, display as an LED display or something like that. It can go on display or 7 segments, etc. Or LCD display, whatever. So I'm not going to explain how to write on the LCD because it's going to be, again, in different courses. And when you go to the microprocessor courses and when you go to the other programming courses, you will call it, I think, embedded systems courses, you will learn how to write on LCD. You will learn how to apply this in hardware. So you will do it in the hardware, make a product or make something like make a real accumulator or make a real program. But here I'm just telling you what's happening inside, just for demonstration. So to give you like a practical example of how to use the accumulator. So let's assume here is the clock cycles, here is the clear button, and here is the inputs. Okay? Now, as a banker, I already have the inputs like this, 5, 4, 1, 2. Before, you see a clear button. So a clear button, you will see at T0, here is T1, T2, T3, T4, T5, and T6. So you will look at these updates, where the updates happening there. Make sure, or let's look when before the clear. That's the first observation. Look at the clear. The clear is active low. Therefore, the clear here was 1. So this will affect here. So what's the initial condition? Since the input is don't know, we still don't know this. Okay? Then a clear button has been pressed. Since the clear button has been pressed, this will make the output 0. We don't care what's inside the input because the clear button has been inserted. So what was money before in that machine before, I don't worry what's happening. I don't need to worry about this because I remove them, then I press the clear button. After removing the clear button, the first update's happening here. So let's assume here the input events don't care. The first update's happening here. And this first update, the update here adds positive cycle, all of them. The clear button still pressed. Therefore, it will still remain 0. Why? The clear button was still pressed. Okay? Clear? Now, let's go to the next update. The next update at T2. At T2, you will see here's 5, right? So it will go to 5. It will be 5. Then the next update, 4. How the answer will be? It will be 5 plus 4 because it's cumulative. So it will be 9. Okay, clear? Then the next update at T4, it will be 1. So 9 plus 1 will be 10. And let's use hexadecimal. So 10 means A. Then the next update here is 1. So A plus 1 equal, I think this is 2, not 1. A plus 2 equals C. Okay? Then there is another 2 at T6. So it will be C plus 2, which is equal to E. Then the end. So the push button will say it's E. After that, make some conversions, several conversions, and convert this to LCD. You will see in the screen as $15 US. Something like that. Okay? Any question? This is another example of some practical applications using the accumulator. Then there is other types of registers. They are called shift registers. Sometimes we have a series data comes in series, but we need to shift them. We need to shift them maybe one step or 2 steps. So how can we shift them? By using the register or shift register. Basically, I need this serial inputs, no change on the information, but I need to shift them. For some reason, like I need to shift them. I'm not sure what's the practical application for this. I mean, it's really been used, but maybe sometimes if you receive something backward, you need to make it forward. Actually, I'm not exactly sure about the practical application, but in case if you need to shift the data, you can shift it in one direction or in both directions. You can shift it from right to left or left to right, which is using the shift register. So the first here in this circuit is shift from left to right. This figure. Left to right. Here is the inputs. Here is the outputs. So the number of flip-flops will tell you how many bits will be shifted. So if we have only one flip-flop, you are shifting the data one bits. 2 flip-flops, 2 bits. 3 flip-flops, 3 bits. 4 flip-flops, 4 bits. So the number of shifts will be depending on the number of flip-flops that you have. Okay? Here in this circuit we have 4 flip-flops. Therefore it's 4 bits shift register. 4 bits shift register. Again, this type of registers is just to shift the data. So the data will be transferred. So let's assume this is Q1 star, Q2 star, Q3 star, and Q4 star. Okay. So I'm gonna draw the following circuits, following sequence. Here is the clock. One, two, three. Okay. And here is the serial inputs. The serial inputs start with 0, then goes to 1, then goes to 0, goes to 1, goes to 0 for the rest. Okay? Then we need to determine Q1 star, Q2 star, Q3 star, Q4 star, which is the same as serial outputs. We need to determine all of this. Keep in mind the updates happens all of them are positive edge. So the update's happening at the positive edge. Okay. This update here, 1, here is 0, 1. Let me write it in different color. Sorry. Here is 1, 0, 1, 0, 0, 0, 0, 0. So the serial input sequence was like this. 0, 1, 0, 1, 0, 0, 0, 1, 2, 3, 4, 5, 2, 3, 4, 5, like this. Okay? And I need to do the shift register. So let's assume that we don't have the initial condition here. This is one problem of it. If there's no clear button that makes all of them 0, we need to have an initial condition. Let's assume the initial condition are zeros. I'm going to assume because there's no clear button. All initial conditions are 0. Okay? So the initial condition for Q1 is 0, Q2 is 0, Q3 is 0, Q4 is 0. Okay? Now let's follow with the Q1. Q1 is the same as D, but the update's happening at the trigger edge, so, right? So at the trigger edge, there will be an updates. So here it will be 1 at the first. Let me call them as this one. T0, T1, T2, T3, T4, T5, T6, T7. At T0, it will be 1, right? Do you agree with me? Then hold until T1. T1 is still 1. T2, it is 0. T3, it is 1. T4, it is 0. T5, 0. T6, 0. T7, 0. Like this. So we have 0, 1, 0, 1, 0, 0, 0, 0, 0. Okay? So we realize that they are the same as the serial inputs. I'm sorry, this is 1. Okay, no, they are different. Okay? 1, 0, 1, 1, 0, 0, 0, 0. Okay, this is the input. Then let's look at Q2. Q2, at the next clock cycle, Q2, I'm sorry, here, Q2, yes, look at D2, which is equal to Q1 star, the next cycle. So Q2, D2 equal to Q2, which means Q2, if T plus 1, I'm going to write it in other colors. Q2 of T plus 1 equal to Q1 of T. Therefore, the future Q of Q2 will be the same as Q1. So, which means Q2 plus 1, we will copy this. It will be shifted. Again, why this happened? Because of this. Q2 of T plus 1 equal to Q1 of T. And here the same as Q3 of T plus 1 equal to Q2 of T. Okay? And the Q4 of T plus 1 equal to Q3 of T. That's why there's a shift. Therefore, when you draw this, just make a phase shift 1. So here is 0, 1. Here, did I say 0? Here, why it says This is 1, and this is 0. 1, 1, 0, 1, 0, 0, 0. Then for the third one, we will move this. So it will be 0, 0, 1. Let me fix my phone. 0, 1, 1, 0, 1, 0, 0. The outputs, the last one, also shift them 1 bits. So which will be 0, 0. Keep in mind I'm shifting each one in the beginning. So here 0, 0, 0, 3, 0, 0, 0, 0. Then 1, 1, 0, 1, 0. So look at the sequence of Q1 and sequence of Q4. You will see they are shifted, right? Q1 and Q4. So that's how the serial outputs will be. That's how we make shifts. Okay? Any question? Now the shift register here, the first drawback of this design, there is no initial condition. So here I assume all of them 0. The second drawback, which is shift left to right. Can I make it shift right to left, or can I make its initial condition? This is another design by connecting a multiplexer. If it is 0, we will let the serial in. If it is 1, we will let D1 happen. Okay, what's the, depending on the selection bits, what's the point of this? The point of it, which is when S equals 0, we will pass I0, which is pass serial in. When S equal 1, according to the multiplexer, we will pass I1, which is, in other words, pass D1, or like, for example, I just said D3, D2, D1, D0. Those are bits predetermined, or actually here, D1, D2, D3, like this. Okay, what's the point of passing those? Why we add this? We can say D1, D2, D3, and D4, etc. All of them are initial conditions. Those are initial conditions. And these initial conditions, we can, for example, if we press clear, everything will be 0. But if we put the initial conditions like this, so we will let the initial conditions run first, so I can know what's all of the outputs. Then after that, I can run my serial in. Okay, what's the point of using this? Imagine that there is an operating system. When you press restart, the system will restart. But at the same time, we don't want to erase everything. You need to have some data comes from the operating system. So you can see the windows, you can see the programs or the desktop. Or like the booting of the computer will take some time. Then it will be ready to use. So during the booting process, the first point, what will happen? Everything will be clear to 0. Then there will be some initial conditions, which is the built-in data or built-in software that should be essential to let the system work. After that, you're ready to work on it, so you can use your computer whenever you want. Okay? So this looks like, if you need the operating system, it can be used especially like, for example, for the operating system. So we have some initial data that you need to get this installed. Okay? So here's some modification. There is a serial mode. This can be used to shift data one bit at a time. What's the point of this? If we don't want every time to shift the data, if we want to shift the data for a small period of time, then we can use this design. Because we know the clock cycle is keep running. I cannot stop the shifting. I need to use to shift for maybe 3 or 4 period times, like T1, T3, T4. But at the same time, I don't want this to be happening frequently, many times. I would just want this to happen once. Which is we are using this design. We have the shift control ending with the clock. The shift control, which is basically, I'm pressing a button, I want the shift now. After I end, I make the button off. So that's what I did here. Push the button on, then push the button off. That's the period of that I want to make a shift. Then the clock cycle, even though it's still synchronous, but we are taking only small part of it. So this will go to the registers, then we will store only a small amount of that, or we will make the shift for a small period of time. Okay? Any question? All of them are still like here. I'm giving you some devices. Like this is device shifts register. This is parallel register. This is device for with enable, with load data, with write or read. So all of them, like we can consider them as just a special device or a special integrated circuit or IC for the system. This is a design that can shift left or shift right, depending on what you are enabling. So there is a button or an input called shift lefts. If shift lefts equals 0, then right will be 1. Then what will happen? We will move from right to lefts. If shift left is 1, and this will make right 0, then we'll move from right to lefts. So they are just the opposite of each other. So there is a button, it's called shift lefts. It will tell you if you make it 0, you will shift right to left. If you make it 1, left to right. Okay? So there is serial input for left, serial input for right. Then using this design, we can do like this. Okay, so let's talk about the serial addition. So if we have 2 registers and you need to make addition, connect them to full adders. So there is sum and carry bits. Then make sure that to store the carry bit in a storage element so it will be updated for the next one. So here we can add data that can be fun. We can use this design to make addition depending on the inputs. So if we have this input, next clock cycle make addition, the other clock cycle make addition, and so on. So we can say each bit has okay, let me discuss a little bit about this. Okay, what's the point if using this part, shift register? Why we didn't use, let's assume we have 4 bits, 4 bits adders for A and B. In A, 4 bits, as we know, A4 or A3, A2, A1, A0. For B, B4, B2, B1, B0. So how many bits we need? How many adders, full adders we need? We need 4 full adders, right? As we see this earlier, even in the exam. Each bit needs full adder. That's what we know in the combination logic circuits, right? Now, if we use the shift register or if we use the registers, it can be easier by using only one full adder other than using multiple adders. So here, using registers, we need one full adder. How? We have, for example, these bits, instead of adding them as parallel as A0, A1, A2, A3, we will add them as a serial inputs. A3, A2, A1, A0. Each one will go by a clock. Will be updated by a clock, and that's what's happening. So we can make them, instead of being parallel, they will be in series. Then each one will be added. Then we add a shift register. So let's go to the next. A0, shift it here to be A0, A3, A2, A1. Now I can add A1, then shift it. It will be here A1, A0, A3, A2, then shift it, make the addition A2, A0, A2, A1, A0, A3, then make the addition A3, A2, A1, A0, then you have the control to stop it when it reaches back to A0. That's how we make the addition. So we can have sum and carry, then the carry will be stored into this to go to the next cycle. We need the carry bits to be stored so we can use it for the next cycle. We will not keep it like as a feedback, because we are all here waiting for the next cycle to make the other addition. Wait for the next cycle to make the other addition. Therefore, we need to have a D flip-flop there. How we can design it, I think we don't have enough time today, so next lecture I will continue in how to make the design using this. Thank you.